Hi, I'm David, and I'm presenting information-directed reward learning for reinforcement learning. In common reinforcement learning tasks, such as playing video games, we usually assume a fully specified reward function to be available. But in many practical applications, this is not the case. Because of this, there has been more interest recently in learning a model of the reward function from human feedback. But interactions with humans can be very expensive, which is why we want to do active learning in this situation. So there's been some prior work on active learning in this context. However, previous approaches are either only designed for very specific query types, such as comparisons or numerical evaluations of full trajectories, or they use approaches that uniformly reduce uncertainty over the state space, which is not aligned with the goal of RL, which is ultimately to find a good policy. So let me illustrate this last point in a simple example. Consider this robot, which wants to collect food from the grid world for a human user. The robot can only walk 4 time steps, so it has to decide which of the food to collect. But the robot does not know which food the user prefers, but only the user knows their preferences for the different items. Now the robot can ask the user about a specific item, and the user will respond with the value of this item. How many queries does the robot have to make in order to figure out the best policy? If the observations are noise-free, it can solve the task using 4 queries by simply asking the user about all items in the environment. This is what classical active learning approaches do. But it turns out the robot can do much better if it considers the environment dynamics and uses them to decide which things are important to query. And this is what our information-directed approach does. So if we assume that collecting more food is always better, there are actually only 2 policies that are potentially optimal in this environment. Either collecting the cherry and the apple, or collecting the cherry and the corn. Importantly, the cherry will always be collected because it is on the way to collecting something else, and the pear will never be collected because it's not reachable from the robot's initial position. This means that the robot can find the optimal policy here with only 2 queries to the user, namely asking about the apple and asking about the corn. So it can reduce the number of queries necessary by half by considering the environment dynamics. So let's now move to our more general setup. In normal reinforcement learning, the agent interacts with an environment by taking an action in a given state, and the environment returns the next state and a reward signal. Instead, we assume that the environment does not provide a reward signal directly, but that there is a user which knows something about the reward function. The agent can make queries to the user, and the user responds with information about the reward. These queries could, for example, ask for the return of a full trajectory, or they could ask the user to compare 2 states. We provide a general method that works with a wide range of different query types. Now, throughout the interaction with the user, the agent can learn a model of the reward function denoted with R hat, and then it can use this model as a replacement for the environment's reward signal to run any RL algorithm with. We assume that interacting with the environment is cheap, but asking the human about the reward is expensive. So the key question we're asking is, how should the agent select which queries to make? Next, I'm going to introduce our information-directed reward learning algorithm, and I will first introduce the main ideas by revisiting the grid world example from before. So what we observed there is that if the agent considers potentially optimal policies in the environment, it can infer which states it has to query about to distinguish them. Our method encodes this in a general acquisition function to do active learning with. The first step to do this is to consider 2 plausibly optimal policies, as we did in the example. Then we can think of the goal of RL as being to distinguish these policies to figure out which one is optimal. So we can ask the question, how do pi1 and pi2 differ? And we can answer it by considering the difference in expected return between these 2 policies. In our example, the return of pi1 is given by the reward of the cherry plus the reward of the apple, and the return of pi2 is given by the reward of the cherry plus the reward of the corn. We can see that the difference between the return of the 2 policies only depends on the reward of the apple and the reward of the corn. So the final step of our method is to select observations that help most to distinguish these 2 policies, and we formalize this using information gain. By selecting queries that maximize this information gain objective, we select queries that are most informative for distinguishing these 2 plausibly optimal policies, which is the objective of RL. So there's one component that is skipped over here, which is how do we find these two potentially optimal policies in the first place? In our algorithm, we essentially combine two ideas to do that. The first one is Thompson sampling, where we sample a set of reward functions from the agent's current belief, and then we find policies that optimize for these samples. This gives us a set of candidate policies that represents the agent's current belief about which policies are optimal. To select two policies from this set, we then maximize the entropy of the difference in return between pairs of policies. This gives us the two policies that the current model is most uncertain about. Finally, let's put all of these pieces together and let me present to you the full algorithm that we call information-directed reward learning, or short IDRL. First, we initialize a Bayesian reward model and obtain an initial set of candidate policies using Thompson sampling. Then in each iteration, we first select the two policies with the highest entropy in the difference of their returns, and we then select queries that maximally reduce our uncertainty about these two policies. Then we make a query to the user and update our model. Now we repeat this loop, where maybe for computational reasons, we do not want to update the candidate policies in every iteration. Ultimately, when some convergence criterion is reached, or we have exhausted a budget of queries, we can stop the loop and then return a policy that optimizes the mean estimate of the reward model. We consider two implementations of this algorithm, one using Gaussian process reward models and one using deep neural networks. If we model the reward as a GP, the rewards are jointly Gaussian distributed. Also, because the expected return of a policy is a linear function of the rewards, it is also Gaussian. And so we can compute the entropy and information gain we need exactly and efficiently. Also, we can sample from the posterior to implement the Thompson sampling step. In our experiments, we test this implementation with numerical evaluations and pairwise comparison queries. Second, we study a deep RL setting in which we integrate reward learning into a policy optimization training loop. Here, we use a neural network feature representation combined with a Bayesian linear model as a reward model. We can train this model from pairwise comparison data using the Bradley-Terry observation model. Also, because the Bayesian model is linear in the feature representation, we can still approximate the IDRL objective efficiently. So let me next show you some experimental results using this algorithm, starting with the GP-based implementation. The first environment we consider is this simple driving simulator, which was proposed in prior work. Here, we learn from comparisons of trajectories, and we evaluate the regret of the learned policy after a fixed number of queries in the left-hand plot, and also the cosine similarity of the learned reward function with the underlying linear true reward function in the right-hand plot. We compare information-directed reward learning, our algorithm, to expected policy divergence, which is a prior active reward learning method. We compare to uniformly maximizing information gain on the reward to select queries. We compare to maximum regret, which is an acquisition function that is designed for this setting where we compare comparisons of full trajectories. And we use uniform sampling as a baseline. Here in the regret plot, you can see that IDRL can learn a good policy faster than the other methods. In this simple environment, you can also see that it learns a similarly good reward function measured in terms of cosine similarity. Next, here is a more complex environment that we designed in the MuJoCo simulator. The swimmer has to move to the green square in the corridor. The underlying true reward function that the agent doesn't directly observe rewards the agent for moving forward before the goal and rewards it for moving backwards if it's past the goal already. The reward function is linear in a set of features, and we use an off-the-shelf RL algorithm to solve the environment. We also use a fixed exploration policy to explore the environment, and the agent can query clips from the exploration trajectories to observe the sum of reward over these clips. Here the same plots as before again, regret and cosine similarity of the reward function after a fixed number of queries. We compare similar algorithms as before, but we add expected improvement, which makes sense for these numerical query types, and we don't compare to maximum regret, which does not make sense for the numerical query types. Also, we don't compare to expected policy divergence, which is computationally too demanding in this setting. IDRL is able to learn much better policies with a small number of samples in this environment. But in this environment, there is actually a trade-off with learning a uniformly good approximation. So the final reward function learned by IDRL is a bit worse as measured in terms of similarity than the ones learned by some of the other methods. However, it leads to better policies, which is ultimately what we care about. Finally, we test the DeepRL implementation of IDRL, also in MuJoCo environments. So in this plot, we show the score that the learned policy achieves averaged over multiple of the standard locomotion tasks in MuJoCo. The reward model is trained from synthetic comparison queries that are provided using a fixed schedule. Our implementation of IDRL uses queries from rollouts of the currently optimal policy, but also all candidate policies that it considers. The other methods, of course, don't have access to these candidate policies, and therefore we consider an ablation of IDRL that only queries from rollouts of the currently optimal policy. We compare, again, to maximizing information gain to select queries and to uniform sampling as a baseline. The results show that IDRL can learn, again, better policies from fewer queries than alternative methods. So let me summarize the key takeaways. IDRL provides an acquisition function for actively learning reward functions that is focused on determining the optimal policy. It can be implemented exactly with GP models and also be approximated for neural network models. We saw that IDRL improves the sample efficiency in various environments in our simulated experiments. IDRL is also more general than previous methods because it can be used with an arbitrary Bayesian reward model and arbitrary query modes. So if you want to learn more, feel free to come visit our poster or read the full paper here. Thanks a lot.